All right, I'm getting in heavily to this constant, and again, I'm just trying to reiterate that it has something to do with the the hard problem of consciousness, the zombie philosophy, and it's also called the Boltzmann brain, because you need to have or because a having a Big Bang out of a singularity, which is technically like reverse entropy, like reverse catastrophe or catastrophic extinction or something like that, and reverses life out of that. That's like technically what singularity Big Bang is, and a vector, so to speak, or you can have a zombie brain, or it's as likely that's as likely as you being a brain floating in space. So uh, it's also like the zombie argument because, or the zombie philosophy, or the hard problem of consciousness. I'll have to catch up on the video. And yeah, so you have to be able to perceive it as there are zombies in space, just like you. There's a mirror image of everything in this universe and another universe, but everything that does have consciousness does not have consciousness unless you choose to give it consciousness. But if you choose to give it consciousness, then you are saying that there is hereticism, essentially, or neuroticism in the universe, which is obviously not true. But if you go a step further and say that it is more likely that I am a brain floating in space, you still stick to uh, hereticism. You still have feelings, you're still conscious, you're still reacting, but you go one step further and say there is a double constant in that in this, or you go to the many worlds and you say that there is a you in the many worlds you can say that there is a double constant, and that that basically one of those constants is the zombie philosophy, or the brain argument, the brain and the Big Bang argument, or or the vector argument, and the other argument is that there is, sorry, what was I saying? Right. So the other argument is that everything on the conscious evolutionary uh, evolution tree, everything that is conscious technically, all the way down to oysters, that is like everything non-vegan, pretty much. It's, theoretically has consciousness through neurons, and then you say that that is another constant. So you have a second constant. Again, this is a constant squared argument, and you could call it QE because it's like quantum, or sorry, QR because it's like quantum reality. You can call it QR because it's quantum reality, but I'm just saying it's not going to fit the bill because it's a perceived notion. And then you have that in mass because conscious beings have real mass. So when you eat anything conscious, you are technically just eating conscious things, just like a zombie would. Bad brains. All right, I'm going to practice. I'm going to practice my basically my argument against a unified geometry or a geodesic, and my argument against a geodesic. Basically, now it has string. It has string theory, and it has a vector coming from a vector coming vertically, and then it's called Mexican hat theory. So the vector at the top of the the hat is the vector for the Big Bang, and it precipitates. Can't stop saying that word into basically the hanging threads are the strings, and those strings are what keep the the geodesic uh, in one sense, but you also have like uh, dark matter bars and gluon, muon, and uh, gluon, muon, and sorry, neutrino strings inside particles, so inside matter. And I would just say call it something like double umbrella theory. And so double, I'll just practice it. Double umbrella theory instead of like a three-dimensional hexagonal rectangle. You just have like two wider, I guess two umbrellas. You know, two umbrellas. They could be horizontal or vertical, essentially, if you're dealing because you are dealing. That's the gravity magnet, electromagnetism theory. And I mean, it seems kind of easier to work with it from up and down because you kind of know logically that's how gravity works. I'm just trying to point out, but of course it has to have, and it's like a force of distance could be the Minkowski space, or like the horizontal infinity, and yeah, so I was basically all right. Sorry about that. Yeah, I was trying to create a vector like in my mind and understand how if I was looking at like basically how if I look at the sun's in one point, the sun's in one point, but it's obviously its rays are streaming completely spherical around me or uh, contripical, like contripical and centrifugal. So that's how the rays, when I'm looking at those rays, that's how I see it because it is magnetized, and those are how the lines align. Especially if you try to look at it for a little bit, then or a second or two. That's how the UV gets so bright, and you can see the centrifugal and centrifugal forces attached to that. So I'm kind of trying to observe um, this idea. I kind of lost this other. I mean, I kind of lost the middle name, but the last name would just be like you have two of these vectors on either side. So I guess I am working with it horizontally, and your infinite space would be vertical. But you have two vectors on either side connected through force over distance or Minkowski space is what I believe it to be. And then you correct me if I'm wrong, but then you have sorry, you have yeah, two vectors. Okay, all right. I'm saying those are obviously tangential happenings. I'm also trying to create like a waist theory because this is just what how I would see force equals. Sorry, not force. Work equals force multiplied by distance. So you have your force in an arrow one direction over a distance, and you just do to the negative one exponent, and that's inverse property of it. So an inverse of a waist, like if you inverse a waist theory, you basically have a connector vector or a particle connecting a vector, or a double particle connecting a vector. Um, Essentially, like how I was trying to explain, like an inverse of the wave function or Young's wave, if I'm saying that correctly. Please correct me if I'm wrong. And then you just have like so two arrows are pointing together, and this is like the inverse of like a waist theory instead of essentially like an entropy, okay, if like your entropy is like essentially your waste, but we know that entropy is only happening, entropy is getting bigger. So I'm saying, in your cosmological constant of entropy, entropy is getting bigger. So in that sense, the universe is expanding, but it's not really wasting anything. It's just recycling. And in a waste theory, like if you have like a double umbrella instead of a geodesic, or instead of a sphere with black holes precipitating the recycling or ingressing the recycling, you have this dressing that just looks like a double umbrella, and you have to have obviously like an empty space. So it doesn't have, it's not an infinite universe, but it's not a completely unified. Um, it's not a completely unified theory, just because it does have like essentially, uh, I guess, gaps, and those gaps, like if you have upsilon or like two deltas at a if you have two deltas at your double ultima, okay, two particles or two photons at the center, and you had two just essentially like U's of waves, but those would be essentially like the corners of like the universe. So it essentially is a hyperboloid in a sense, like universally, that would be the mechanic, but it's the inverse of a hyperboloid. Okay, so it's the inverse of a hyperboloid. It looks more essentially like an hourglass. Like if you look at a hyperboloid, you can see it goes in and then it goes out like a cylinder with a small cone. But I'm just saying, if you expand it from, well, I should say, if you expand a hyperboloid, if you expand a hyperboloid, you split it down the middle. I don't know exactly how you do that, like a delta over two. You divide it by, you split it down the middle like a delta over two, and then essentially, you have your horizontal with a whole like the inverse of a hyperboloid. When you break it out, it'll essentially be like a really kind of crazy looking hourglass, like just hourglass with like an insanely tiny. It'll just create so much more time, is what I'm saying, exponentially, because the amount of sand you would have in the top would take so much more time to go through it. I mean, it'd be like 1 second compared to like uh, 40 minutes or something like that. I'll say like 50. I'll say an hour, just something like that. Sorry, no, I shouldn't say 1 second, but like, it'd be like 10 seconds. It'd be like 10 seconds. All this sand would get through because it's just going to fall through, basically a hyperboloid in a constant infinite universe, like a geometrically unified geodesic, whereas in like an insanely long hourglass, this is going to take so much longer. So you just gain so much more time, if you inversely, if you negate the energy around a hyperboloid, and you expand that energy and create that energy as the boundary for essentially the hyperboloid turns into empty space. And that empty space, I know this probably can never be. I know it's like, I don't know. I mean, essentially, like, I don't think people want to look at a asymmetrical universe. However, I'm just saying it basically breaks Einstein's. It seems like Einstein's symmetries, supersymmetries, if not, and yeah. So you can have like super rotations, but or it can even manage something. You can even say that the hourglass is managing um, like a really small amount of time inside the hyperboloid, inside the celestial sphere, like in the celestial holography, and it's all that just dark matter. Essentially, that would be like an insane amount of dark matter, in my opinion. So, all right. Yeah, I heard Gary Mosher says like light was originally it's 300,000 miles second. I do like I would like to distinguish maybe I would like to distinguish yeah I would like to distinguish maybe 10 meters or per second, and if you do have if you do have 10 meters per second, okay, that's per second. You just, I mean, it's just the estimation, or it's just a, estimation of. I mean, it's like a double dot. It's like a double dot formula or a double ultimata formula where you just say, okay, I have a set. I mean, this goes along with Boltzmann brain argument too. I mean, even if you say it's vector, if it's complete vector space with empty space and black holes, or like Minkowski space within sorry dark matter, uh, and you have 300,000 kilometers, 180,000 meters per second photons that is traveling through. That could probably be your brain theory, essentially, because when you have the Heisenberg unknown principle, you are essentially getting something equal to, well, I'll say this intuitively, but you're essentially getting something equal to or greater than essentially the greater theory, or the more logical perception is you could have something going like I don't know, 100, say 1,000 meters. I mean, it does 180,000 miles in 1 second in the amount of time that you allocate what 1 second is. I'm just saying there has to be uh, a real congenial understanding that what happens in space, what happens in the subatomic particles, is not going to happen in real time with you as you are observing it, but you are still the observer, and you are still like essentially through the experiments of the boson and the LHC or LIGO, essentially those experiments work in that you are going to have uncertainty. You'll have uncertainties in your particles, and it doesn't make it really. I mean, it really is sound to say that the uncertainty is sound. So just because because you give it a double center maxima doesn't mean that it changes. I meant to say double center maxima or double ultima. Um, Particle like a proton, like a plus and a minus in permittivity, magnetism. It doesn't change the fact that there's still fluidity in light traveling within that time. I mean, it's a double constant. It's a constant squared. So, and your mass is whatever the mass is, or whatever the subatomics are doing to drive to work for the work. So anyway, like force multiplied by distance, and trying to get into like trying to get into like I mean, if you look at an hourglass and you say, like, if you look at the globe, okay, you look at the globe, we're going to pretend the moon's there, but we're not really going to think about it, which is still important. I mean, even in terms of that, you could still have hourglass, like a, I don't know how to really describe it, because you're not going to have an hourglass only works with gravity, so it's kind of hard to say if you obviously let like a bunch of sand go off like in the torsional glass fixture of the hourglass, and you let those just like float around back and forth, and you understand that there's two accumulative like umbrella shape, like opposed like opposite inverse umbrella shaped. So it's an hourglass that wraps around. It's an hourglass that wraps around the Earth, sort of like an umbrella, and then it works in this way, and you have this hourglass, and then but that hourglass moves around with the orbit of the moon. So the moon is orbiting along on a exact fixture, but obviously you have like this gravity. Um, I mean, I would say obviously the moon is helping drive uh, the rotations and not so much. I mean, and then the sun is helping drive the revolutions. And if you pretend like every time the fixed moon, because the moon is always facing us, so every time the moon is facing one point, directly opposite of that, there is like this hyperbolic, or it's actually what is it? Actually, it is a hyperbolic or a hyperboloid, but it's like an hourglass, and so that I mean, it's like an hourglass, and that hourglass obviously has like the center, so it'd be kind of like a M, like a M, uh, or like two vectors, two triangles, which is also sort of like the opposite of how you get your Einstein ring. Essentially we know that there is for certain an Einstein ring, around the moon, but how is that? I mean, are we talking about orbits? Well, they're not saying that the orbits do anything, so they're just saying that the orbits. Yeah, I mean, I've seen Einstein rings, but I don't know really. I mean, you really can't prove that. Well, I should try to prove it, but yeah, I've definitely seen Einstein rings like in permittivity in the blue sky around the sun. So you're looking at the sun, okay, and that sun is hitting you at a certain vector. Your energy is allocating all of that sun's energy, and it's just the photoelectric effect because the um it's not. I mean, is it photosynthesis? How there is just a reflection off the Earth, and obviously the tightest part of the sun that is it within your vector is going to hit your direct spot. And again, I'm just talking about these time glasses on the opposite side of the moon as just a plausible theory of how it's like rotating so fast. And I'm just using like hourglass because I thought it was like a good metaphor to have, since it would just be continuous time. If you just put sand in either side of the time and it always had to go in orbit with the moon around the Earth, like, but it was obviously totally curved within a structure that it would be able to fit around the Earth. Like it would just stay in permittivity the whole time. It sort of stay in Heisenberg unknown principle, and just be an eternity in Jesus in infinities, I guess, but calculated. Then you have just all your sand. Like I said, you just put like a few particles again on the opposite side, the closer to the moon. So the closer that you get to the moon, the smaller the hourglass gets, and the further you get away from the moon, the bigger the hourglass gets, and essentially all the sand is stuck in there. Um, but you could realize, especially in a simulation, how the sand isn't going to ever get through, even though the Earth is if the Earth is rotating well, is it in the atmosphere? Because if there was like essentially like something like an hourglass that wrapped around and it was a hyperboloid, and you had the Earth's rotation, and you had the hourglass essentially. as the Earth rotates, 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 obviously all the sand would eventually permeate through, and that is kind of like your super rotation, like an example of what your super rotation would look like anyway. An example of what your super rotation would look like. But that was really drawn out, and I'll have to practice that one. But anyway, like I said, the sun is reflecting, it's beaming through, it's reflecting off the Earth. I mean, obviously, radioactive decay is happening more and more and more, even with reflection. If you consider photons, and if you consider the photoelectric effect, and you consider uh even 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 I think Bohr's model, and obviously that vector is going to be tight because that vector is real. That vector is through dark matter essentially. And I mean, you could even, if you even posed a hourglass, if you have this double hourglass, um, you just make hourglasses around, essentially massless hourglasses that stay in rotation. So obviously these hourglasses, when it rotates, since the Earth is, well, except for the suns would always stay in permittivity with, or the Earth would only always stay in permittivity with the suns. So these two hourglasses are basically the force, okay, or I should say the work, which is the distance, or yeah, sorry, the force doesn't matter. The force multiplied by the distance. So you could just say the force is, or you could just make a bunch of hyperboloids essentially out of hourglasses. So that would be my theory on hourglasses and how they're good simulations for permittivity or dark matter or magnetism or electromagnetism or what have you. But again, I'm just saying the sun permeates, like a waterfall. It gets weaker and weaker by the time it hits, and by the time it hits, it just reflects off what it can. But there's so many particles, 10 meters per second, and you're observing this, and you're saying, why is the sky blue, and why is the sky, getting darker and all that? And it's because you're losing your field, and essentially essentially what happened is you're seeing less and less sun, so the angle so the vector of your sun is getting less. It's not getting less and less, but it is curving. The vector of your sun is curving essentially because of the angle. um well, if you were to see it from outer space, you'd see the curve, but you can't see the curve from here. So the horizon is curving, but you don't see that far. So it's curving, it's curving, it's curving in that vector. Essentially, essentially what the math, essentially, or it's just a parabola, or sorry, a parabola, like a parabola or something, and it just gets smaller and smaller and smaller. Again, and it's curving around that space, curving around that curve, and then it just disappears. And so that's you losing that essential photoelectric effect, and there's no more photons beaming through dark matter, and then you have your sun. That's the completion of your sunset. Uh, but my point would be is if you're looking at it at say 12 p.m., you're looking at it and you still have a vector. This vector is well, I'm trying to create an Einstein ring here. So this vector, okay, that you see, the sun is beaming from its width, from its diameter, it is beaming a vector directly to you, okay, 180,000 meters per second, and the reason it's not Einstein, it's not gravitational lensing. You could say it's gravitational computation, because you understand, if you have if because you understand through reflective lensing and the editing experiment and the moon being so enlarged from the reflective lensing to not being able to enlarge the sun because of reflective lensing because it's too far away, or the sun being much bigger than the moon in a solar eclipse, like 3 times the size of the moon in a solar eclipse. Um, but when you use reflective lensing, the moon is bigger than the corona of the sun, and you just get like a little, you get like some solar flares and things like that, but you actually get like a massive corona in like a real solar eclipse like this was back in the day. And so this vector, and so you see, so you understand just through that, just through the Eddington experiment. Unfortunately, well, I don't mean to say unfortunately, but yeah, because it's right, because Einstein was right. So Einstein was right. So you have a a vector shooting towards you, and through the Eddington experiment, you would understand there's another vector going behind that, and you can understand that vector is super rotational, and you would understand that that's a ring, and you even see that ring during the day. You don't even have to be looking at the moon, but you understand it as a vector, and then um,
All right, this is gonna get a little sloppy, but basically the gravitational lensing. All right, so you have your reflective. You have like a reflection through the photoelectric effect. That's why you see the sun um, in the blue sky because it pierces through in a vector directly. How you see it. That's how it reaches you. That's how you observe it. So that's how you have to be consciously aware of it. And I'm gonna sort of elaborate or collide this into the Heisenberg principle. So anyway, you have your vector space, and that's how Einstein figured out his gravitational lensing because he made a vector behind the sun. You can clearly see like a ring around the sun when you see it. So because it's a super rotational 360 degree vector in that sense is what like is the vector like so essentially in your reflective lensing. That's why you're seeing outside the gravity. So the reflective, like if you were looking at through a seriously power reflective telescope, then yeah, the sun would be pretty big. But isn't as big as the Einstein ring isn't as big as the vectors because you're obviously the observable. So technically, that ring is pretty massive. But again, you don't you see it from where it's at in the vector. You don't see it where it's at in gravitational lensing. You don't see it where it's at. And the Einstein ring is actually around the sun with another vector behind it, but that's not how you see it. You see it gravitationally, um, and therefore your perception is skewed because it has to the photons have to reflect, and so again, that circle is forming when you look at this when you look at it like if you look at the sun after a rainbow. A lot of the times after a rainbow, you can see like it storms and then it gets sunny. Maybe that's when like the air is most energetic, like electromagnetic after a storm. Um, I feel like that would be before though. Uh, anyway, when it rains, the roads are slipperiest when it first starts raining because that's when the corroded oil like orients itself and it becomes a liquid and right away. So that's when it sort of hurts the most. Or if you like were burning or something, it would hurt the most initially. That's kind of like the stretch of uh, like a reaction, like a jerk. And so I'm going with that because I don't think the vector would be. I think the vector is directly outside of the sun. That's the perception. The vector is directly outside of the sun, and the Einstein ring is directly outside of this. The Einstein ring is directly outside of the sun, but you see it gravitationally. So there could be a gravitational pull. It could just because through the reflection, obviously off the Earth. So from where you're standing, that'd be observable, and then that vector would reach just inversely to the other side of how if it like it's like 90 billion miles sorry, correct me if I'm wrong, but 90 billion miles to get to the sun. It'd be another 90 billion to get to the end of the other vector. And then the Einstein ring would be around where the sun's position. In a colloquial sense, or in a logistical sense, but in a colloquial sense, you're seeing it a lot closer because of the reflection, because of the photoelectric effect that is hitting, that is piercing off the, that is penetrating, like and reflecting off of the, you know, off of the Earth and back into the atmosphere. So you see it as a double like mirror, like illusion, and that's Einstein's rings. But then I'm also saying, because in Heisenberg principle, you have an x or a coordinate. I mean, this a lot of this stuff, or you have like chi, which is a coordinate, and this is kind of like Heisenberg principle is kind of like an observable for idealism, or like a double consciousness theory, almost like a panpsychic universe. Uh, like, because in a pan, well, I shouldn't say that, because I mean that's essentially the wrong, because you do have an input. So whatever input you put in there would be obviously your natural universe, if you want to call it that. I mean, obviously, I mean Heisenberg principle couldn't be. That was a mistake. I shouldn't have said that. It can't be a an ideal. Well, I was trying to say ideal universe, because ideal universe is just consciousness inversed by consciousness, but in a panpsych universe, there is consciousness inversed by consciousness plus other activity. But in the natural universe, there is, I'd say, only activity, uh, unaware, unconscious activity. So I was trying to elaborate like into Heisenberg, but I mean, you just have wave X, wave P. P is, I mean, these are permittivities or locations from through your telescope, or they could be logistics in a particle accelerator. So it's wave coordinate, wave, approximity, approximation, basically, and what else was I gonna say? Um, yeah, and so that was what I was saying about P. That's what I was saying about Chi. I don't know, like if it's a Cauchy slice, like Sabrina Pasterski's Cauchy slice. I don't know if that has something to do with like there's two approximations, so there's two constants. So she continually says Cauchy slice, and if that has her two observables, then that is her first vector, like her first vector going directly to reaching the sun, and then it's just you have the other side of that, 90 billion miles to get to the sun, 90 billion miles to get to the other side of the vector. So the sun is in the middle. So the sun is the center of the vector. That makes sense. From your position, and then you have that Einstein ring, and that sort of defeats the case. Uh, well, I mean, dark matter would obviously defeat the case for the Heisenberg principle, I think. Yeah, because the Heisenberg principle is a little. Well, I mean, obviously the Heisenberg principle led to the Schrodinger. So I mean, the Schrodinger is pretty. Schrodinger, like I thought. I mean, this the second part of what I'm seeing in the wave experiment makes more sense. Like I kind of wrote over it, but it's like energy, and it's like a gasket, and you have like an input of what you want to turn it into, and you have a well, you had like what like the squirt and the constant for. I can't really get into all that. I totally uh chicken scratched over that, and well, I should say yeah, I just scribbled over it. So yeah, I don't know what I got. I don't know what I got. I think that's about it. Yeah, because yeah, I couldn't get too heavily into the Heisenberg principle, but sorry, I meant to say the Einstein ring equation, which is 4G4GM. I just had this written down. 4GM theta, which is a wave, 4G. I mean, they call it 4G, but they're like saying like that's like gravity, how gravity's hitting and stuff. But that's just four dimensions of mass in your theta, which is your wave, multiplied by energy. Okay, multiplied by energy. So you have four distinct dimensions through these two vectors. You have the ring around that. That's a it's basically the inverse of a hyperboloid, or sorry, it is an inverse of the hyperboloid. It's like kind of like a galaxy actually. Like the 2 points outside are orbiting, but obviously, uh, I'm just calling them hourglasses and things like that. You have a squirt. I'm not going to get into squirt today, but then you have your inverse property, and so this is for the Einstein ring. I was saying the input was for the Schrodinger, but it's like the Schrodinger, as someone said, is AB, but it can't. The universe can be AB, but it can't be BA. Like it can't be done inversely, it can't be done backwards. You can't use Einstein gravity, sorry, you can't use Newton gravity, so you can't have Einstein gravity or something. Like it has to be. I don't know. That's pretty difficult. It's almost like a work uh, it's almost like a work argument, I'd say. Like, well, I should say a work, yeah, work argument. And then, you have, anyway, like I'm talking about the squirt. I'm not going to really get into the squirt right now, but I'm just explaining the dimensional force and you have like an inverse boroid. So instead of, you have like a really thick, uh, latitude instead of a longitude. So really thick latitude, really thick latitude, really thick latitude, like a galaxy maybe you could imagine. And then um, the longitude gets smaller. Okay, so it's like if you smash two ice cream cones together or something. I think that was a good uh, analogy. And then you got your heavy D. What is your heavy D? I think your heavy D is delta. I think your heavy D is delta. Well, is that the frequency? So the frequency, dark matter, and then just constant squared again. There's that constant squared. So there's again an observable. I'd say even I'd even go further and say 10 meters per second like is your hourglass because you have to have some conscious thought. You have to be an observable in the experiment. You have to be able to understand the just the geographics of the subatomics, and you either get that with delta. I mean, if there's a delta and a theta, so it's so you're trying to equal it out, or your squirt is going to be this you know something that something that grows, and then there's entropy. So and then you just have a constant square, and your constant square for me, I mean, if you have a theta and a delta, I mean, that's like your wave and your frequency. So those are just two, and this is Einstein's gravitational lensing for his Einstein ring theory, and yeah, it's kind of how I'd say that's pretty much how I'd say you figure it out.